we're going to talk about solutions. And everyone's heard of a solution. And they go, oh, well, yeah, it's a solution. You know, it's like you know, sugar and water is a solution, and salt and water is a solution. Yes, all that's true. And so what I want to do is talk about more specifically water solutions. Okay. A solution. Now, the important thing here, this is something that a lot of people miss. I'm not talking about my introductory students. I'm talking about my more advanced students. They don't get this. Solutions can be solid, liquid, or gas, and or solutions of those. Okay, I already mentioned salt and water, sugar and water. Okay. One that you've already very familiar with, but you may not realize it's a solution is a gas in water. Gas in water. Now the deal is uniform appearance. When that is meant, when you say uniform appearance, is that there's no characteristics, no distinguishing characteristics between what's in the solution. Salt and water. Alcohol and water, also known as vodka. Do you see the vodka in the water? Do you see the water in the vodka? No, they're uniform appearance, or they're homogeneous. Homogeneous, that's the big deal here. Doesn't matter if it's solid and liquid, liquid and gas, gas and gas. For example, I'm here sitting there breathing a solution of multiple gases. Most of the gases are nitrogen gas and oxygen gas, but there's also a fair amount of carbon dioxide gas, carbon monoxide gas. I can't distinguish between the oxygen and the nitrogen. Hence, it's homogeneous. Hence, it's a solution. Okay, I don't have a ring on, but a lot of times I will have a wedding ring on my left ring finger. I can look at that, and that is a solution of gold and copper. I cannot tell the gold from the copper. So it is a solution. By the way, the copper is there for strength because gold is very, very soft and it wears very quickly. There's liquid solutions, there's gas solutions, there is liquid gas solutions. The bottom line is it's a homogeneous mixture. The ones we're going to be homing in on today are aqueous water solutions. So things that are in water. So it would be water plus something, liquid plus something, and room temp. By the way, yes, I did do a recording. I'm always paranoid now about that. Okay, so we're doing aqueous solutions and whether they are a solution or not. Now, when we talk about solutions, we're talking about two parts. There is the solute, and solvent. There's only one and one plus solutes. Solvents is the part that's relatively larger. So we were looking at air. It's not an aqueous solution, but it is a solution. Okay. The solvent would be nitrogen gas. Solute would be oxygen, carbon dioxide, carbon monoxide, etc., because those are less than the nitrogen. If we were looking at coffee, solvent would be water, and then the solutes are going to be the, let's say we had cream, sugar, coffee molecules, all 8,000 of them, whatever. The bottom line is the solvent is the water. Okay, so whenever we have a solution, we always have one thing is more than the other. That's the solvent, and there's only one of them. And something else. Now you can have one other thing, or you can have multiple other things. For example, let's look at vodka. Let's look at 120 proof vodka. That is 60% ethanol alcohol, 40% water, and a lot less stuff of things like bad stuff that gives you hangovers, things like methanol, terpenes, a whole bunch of stuff. But the bottom line is with vodka, the alcohol is going to be the solvent. The water is the solute. Whatever's in the most is a solvent. Boom. Okay. And if it's an aqueous solution, that means the solvent is automatically water. Okay. If we take a solid such as table salt, sodium chloride, and drop it into water, glass of water, what happens is, because sodium chloride is an ionic solid, it breaks up into sodium and chloride ions in water. Now remember, there's the SLQ, excuse me, SLGAQ. Okay, so whenever we see the AQ, that's aqueous, meaning ions in water. Now, when I say ions in water, I really mean water surrounding solute ions, and that is the cation and the anion. So let's go back over to here. So I'm going to drop salt into water. We're making pasta tonight, okay? Throw in some salt, throw in some water, get that baby boiling. What does it look like microscopically? Microscopically, we've got the sodium cation surrounded by water molecules, surrounded by the solvent. The chloride is also surrounded by the chloride. Okay, these are called hydrated, and what we end up making is something called a hydration sphere, because it's a three-dimensional surrounding of each of the ions, whether it's sodium, potassium, whatever. If it's ionic, the cation, the positive ion, will be surrounded by water. The anion, whatever that is, will be surrounded by water as well. Those are called hydration spheres. And actually, we can actually even subdivide that into primary, secondary, tertiary spheres, depending on how deep you want the layers go. But bottom line is the water surrounds each of the ions, whether it be positive cations or negative anions. Now, these are for ionic compounds. So you should be scratching yourself, well, how in the heck do we know which is ionic and which is not? Okay, that's what let me do one thing here. Let's take this. Okay, I gave you something called a solubility table. If you go online and look up solubility table, you'll get 20 versions of this. This is the one I like to use because it's graphic. It's one or the other. And when you get into 400, you'll see this gray in there. But for our class, it's either white or black. Okay, when we mix ions together, a cation and an anion in water, and real important, at room temperature, 23 degrees Celsius, room temperature. This is what we get. So when we match an anion and a cation together, we will see where they come together, and it'll either be white or black. If it's white, that means that the ions are apart. So we just looked at sodium chloride. So let's now look on our chart here and find sodium, our cation, and chloride, or anion. And when those come together, it's a white square. White means they stay separate. Okay, so you might be asking, Ferguson, why is this black and white thing we're talking about here? Well, sometimes when the two get together is they don't stay separated and they come together. Okay, so let's go down this list here and look at whether these are going to stay separated or not. And again, when I mean separated, I mean like this, where the water, excuse me, the water surrounds the cation. The water surrounds the anion, chloride in this case, okay? That's white in this table. That means they stay apart. Okay, so let's look at these really quickly now. So we have potassium and chloride. We put potassium and chloride in water. What do we get? There's potassium and chloride. And it's white again. That means that the water will totally surround the potassium. The water will totally surround the chloride. And if we go through every one of these, you'll see that all of these are white and separated by water molecules. Surrounding each. Okay. Now, I want to talk about two forces that drive this. So you should be asking, well, I would be asking, I don't know. What makes one white? What makes one black? Okay. So the black means if we put two things together, they aren't surrounded by water. So let's look at, for example, calcium and sulfate. Is calcium and sulfate totally surrounded by water? No. Why? Because it's black. Okay, Ferguson, what's the deal? What's going on here? What makes one totally surrounded by water and one not? Okay, there are two driving forces going on here, one stronger than the other. Okay, so what are those forces? One is called a solvating. That's supposed to be an A. And the other is a crystal lattice force. Solvating force tears apart the crystal, where a crystal lattice force keeps the crystal together. And this is like your classic video game. We have one evil against another one, and they're battling. Solvating force, crystal lattice force. Okay, if the solvating force, we're going to call it SF, and crystal lattice force, if the solvating force is greater than the crystal lattice force, it dissolves. If the crystal lattice force is greater than the solvating force, we get a solid. It stays together. And that's what this chart does for you. Okay, so if it's black, it forms a solid. If it's white, it dissolves like salt in water, sugar in water. We don't know. Okay, we put the sugar in the water, we can't distinguish sugar from water. Put salt in water, we cannot distinguish between the parts of salt, the sodium and the chloride, from water. Okay, so two forces that are kind of at odds. And of course, the question is what if the solvating force is equal to the crystal lattice force? Kind of one of those flaky deals as well as partially dissolved. Now, solvating force is temperature. Okay, so crystal lattice force is not temperature dependent. So if we want a stronger solvating force, we up the temperature. Gosh, think about this now. You put in your cold coffee, sugar, and stir it around, and you got a bunch of sugar crystals at the bottom. What happens if you throw that in the microwave and heat that coffee up really hot? Gosh, the sugar's all gone. So the solvating force has increased because we've increased the temperature. The crystal lattice force is not temperature dependent, so it stays the same. Okay, so solvating force, temperature dependent, crystal lattice force, not. Now, this is really cool stuff, because we can manipulate now whether something dissolves or not. By how? By manipulating the solvating force via temperature. Isn't that cool? All right, and all of you knew this. Coming into this class, you knew that hot water dissolves more sugar than cold water. You all knew that already. Now we know all the fancy reasons behind it. Oh, we have a solvating force working, we have crystal lattice force working, all stuff. One's temperature dependent, one's not, blah, 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 blah. Okay, does that make sense? All right, now there's no way to look at something and say, oh, that is going to dissolve or that is not. That's why you need a table. That's why you need a table. And I like this table because it's really easy, because it's either black or white, and there's some gray stuff in there that we're not going to talk about. But basically, these guys here are the gray guys here. It's kind of asterisks. But basically, things either dissolve or they don't. Okay, does this make sense?
Yes, it does to me.
Okay, all right, so let's now go on. Monday, I want to talk about what is the equation of when we throw this stuff together. Now, there's another interesting phenomenon. if you are lounging in a tub and it's kind of cold out, say you're at a fancy spa up in the mountains and you're at Tahoe and you have an outside patio with this great hot tub, and all of a sudden the water gets colder and colder, and you start going, well, this hot water is not feeling all that great anymore. So you take a heater, okay, and you plug it into the wall. And is that a problem having that heater sitting next to your spa?
Yes, it could be.
Why?
It could start a fire.
Could start a fire. What else? Now you're in the hot tub.
Electrocute you.
You could be electrocuted. That's right. Okay. So we have and this is very real now. Okay, so we have a hot tub. And we have various salts in the water, all these fancy, exotic, Himalayan salts and blah, 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 blah. Bottom line is we have salt in the water. Now, and it's great, right? We throw in an electric heater. And that electric heater attaches to the power grid in your cabin. So you're sitting there going, oh, I'm getting really cold. I'll plug in this heater. And the cat jumps up on the spa and knocks the heater into the water. Zappo, you are fried. The reason you are fried is why? Anyone have an idea? Everyone knows you're going to be fried, but why? The reason is you have charged ions in the water. Charged ions can conduct electricity. Yeah, sodium cations, chlorine, chloride, anions. Those are charged ions. They can conduct electricity. What's electricity? Everyone uses electricity. Everyone, who's in my lab class, this is what I used to do. Okay, one of the labs we make sometimes is batteries. I go, oh, we're gonna make batteries today. We're gonna make electricity. Oh, wow, that's really cool. Who knows what electricity is? Who's heard of electricity? All the hands go up. And I say, what is electricity? All the hands go up. You guys have any idea what electricity is? Okay, and no one's going to venture a guess. Electricity is the movement of charged particles. If we have movement, we have electricity. Now, within the inside of a battery, we've got a lot of charged particles moving, and that then is transferred to wire, which has got loose electrons, as you know, are charged, and they can move along the wire. So we have electricity. Now, do we have charged particles in that hot tub?
Yes.
We sure do. We've got the sodium and chloride ions. Those are charged particles. When we throw that heater into the water, we can cause those charged particles to move, and there will be electricity in that water. And by the way, if you're sitting in the water, guess what? You get to experience that electricity, which is not good for your body, since your body makes its own electricity, and that's why your heart beats. So, after taking Ferguson's class, you go, gosh, I don't want to have a hot tub with an electric heater by and with a cat running around, possibly knocking that into the water. What if I have a hot tub with just pure water in it? And our kitty jumps up there, knocks it into the water. Are we going to die? What do you think? It's either yes or no.
I'm going to say no.
And you're correct. Why do you think that is?
Without the salt, we don't have the charged ions in the water.
Exactly. No ions. If there's no ions, there's no way to have charged particles moving. Hence, there's no electricity. Now, there's electricity in the heater. It doesn't go anywhere, though. So pure, I'm saying pure water, not purified water, because purified water is pure water, and they add salt back in for taste. But if you get pure water, distilled water, it will not conduct electricity because there are no charged particles in it. Okay, does that make sense? All right, so let's go back to this chart here. So if we have any combination of the white squares, those are going to have solvating forces high enough so that the individual cations and anions are going to be separate, or charged particles are going to be present. Like barium chloride. If we have a spa with barium chloride in it, it's white, meaning that the crystal lattice force has not got them together. So those ions are floating around. Hence, if you've got a barium chloride spa and your cat drops that heater into the spa, you will die because there are charged particles present. However, what if you had a spa with I'm going to say ferric sulfide, but that would stink. Let's do ferrous. No, you can't see it. Ferric sulfide, Fe. SO3. Okay. Now here we have a black square. Now I highlighted in white because you couldn't see the black highlight. Okay, but it's a black square. If the black square is part of your spa, will there be ions present? Think about what that crystal lattice force means. The crystal lattice force is great when it's black. It's greater than the solvating force. Excuse me. So are we going to have free ions running around if it's black?
No.
That's right. No, because they're going to be tied up together in a crystal. So we're not going to have any charged particles because they're going to be tied up as a crystal. So we cannot have electrical conductivity or electricity. So if you're sitting in your ferric sulfite spa, someone dumps in the crystals, nothing's going to happen because they won't dissolve. They'll just sit there at the bottom, but you will not be electrocuted if your kitty dumps your electric heater into the spa because there are no ions present. They're tied up into the crystal. Does that make sense?
Yes, thank you.
So ions present, electricity, conductivity. We can test that with a light. We put in sodium chloride in water and run a current through that, and the light bulb will light. Oops, light bulb will light. Because there are ions present. Ions are present, conducts electricity. Hence, it's an electrolyte. We have strong electrolytes and we have weak electrolytes. Weak electrolytes give a little bit of ions. Strong electrolytes give a whole bunch of ions, or they totally dissolve. Weak electrolytes partially dissolve. Acids give off hydrogen ions. Bases give off hydroxyl ions, OH ions. So again, they're ionic. So acids and bases in water will conduct electricity. So bases are OH, acids are H+. But they're strong ions. Weak electrolytes only give off a little bit of ions. Only a little bit. So going back to our spa metaphor, if we had vinegar, acetic acid, in your spa, and the cat dumped the heater into the spa, you'd get a jolt, but you probably wouldn't be killed because it's a weak electrolyte. Hence, the amount of charged particles available are small compared to a strong electrolyte. Okay, so strong electrolytes give lots We have strong electrolytes. So we have strong, weak, and non-electrolytes. And it depends on how much ions are produced when they're put in water. Now, if we were to change the solvent to something like liquid ammonia, then this whole table would be different white and black squares. But we're looking at water now and at room temperature. Because remember, solvating force is a function of temperature. So we have to specify the temperature when we give a table. Also, solubility is given analytically in terms of grams per unit solvent and all this fancy stuff. You'll get into that in 400. So for example, if we, as a non-electrolyte, if we dumped in sugar, sugar dissolves in water quite nicely, but there are no ions present. C12H22O11 is sucrose. By the way, there are zillions of sugars. Sucrose is one of many, 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 many sugars. But basically, sucrose, when you dump it in water, produces no ions. Hence, it doesn't conduct electricity. Hence, if you had a spa with sugar in it, you'd be perfectly fine with your kitty running around the edge of your spa with the heater going full blast. Because if it got knocked in, you'd still be fine. You'd yell at the cat, but you wouldn't die from electrocution. Okay, all right, let's see here. Okay. So that's what I wanted to cover today. Whole idea of ionic, non-ionic solutions, whether they produce ions or not, whether they form solids in water. Now, let me give you a harbinger of what I'm going to talk about on Monday. Okay, you have to have this chart handy. Let's say we have a beaker of silver nitrate and water. These are all water solutions now, right? And we have a beaker full of salt, table salt. Now, silver nitrate. So we have silver, where's silver? And we have nitrate. Silver nitrate's white. That means this. We have silver ions, nitrate ions in water. They're not together because the crystal lattice force isn't strong enough to keep them together. So the solvating force tears them apart. And we have sodium chloride as well. Here is chloride, some chloride. Okay, what happens when we dump this into that? Now we have a mixture of 4 ions. 4 ions. Okay, we have sodium and chloride and silver and nitrate. So we have 2 new combinations that weren't available before. Okay. We have the new combinations are sodium and nitrate and silver and chloride. Okay, so we have to consider those new combinations. The new combinations now are sodium and nitrate. That's white, so nothing basically happens. They still say dissolve. So the solvating force is great here. Excuse me. When we have silver and chloride, it's black now. So really, we don't have this situation. We have this situation. So the sodium and the nitrate are still apart because the combination is white, but the silver and the chloride are black. So that crystal lattice force is very strong. It keeps that crystal silver chloride together. So that's going to form a solid. So really that's what, and it happens to be a white solid. So back in the old days of CSI, one of the tests for chloride present is to put in some silver. And if you got a white precipitate, we know that chloride, bromine, or iodide are present. Normally it's chloride. So it's a very strong test for chloride when we put silver with it. It's a very strong solid. That means the crystal lattice force is very strong with silver chloride. And then there's some associated equations we have to balance with all this stuff. Okay, so that's what happens when we put stuff together. Sometimes we get a solid, sometimes we don't. But if we start with two solutions that have no solid in them, we put them together, we have new combinations. And on next week, I'm going to talk about different kinds of reactions, and this happens to be a double replacement reaction, because we've actually replaced the chloride with the nitrate and the sodium with the silver. So we have basically two new combinations. And those two new combinations may yield a solid, or they may not. Just have to look at the table. It'll tell us. Okay. So what do you guys think of this?
It's not bad so far.
Good. Do you find this interesting, this whole solubility stuff and ions and stuff? It's very practical.
Yeah, I relate to it more than some of the other stuff we've covered. The more mathy
like
things.
the mathy stuff.
Yeah.
I agree. I think this stuff, because you're gonna, you know, in 5 years from now, you're gonna remember this. You're not gonna remember all the math. You're gonna remember what a pain it was the math. This you're gonna go, oh, now wait. If I increase temperature, this is gonna dissolve more. Why? Because this is gonna happen. Stuff. You know, it's real useful. Really is useful. Okay, so we are going to stop here.